Hi there, welcome back. So today I'm going to show you how to set up an unsteady flow model in HEC-RAS. So we'll use today's case, the study area I have selected. It is somewhere in Canada. You can see here in the figure that we have one lake, St. Martin, and another lake is Big Buffalo Lake. So these two lakes are connected by an artificially constructed canal, this one called Rich 1. So we'll have our survey data for this cross section of this lake and this canal as well. So the idea is to test if the canal is appropriate to carry water from Lake St. Martin to Big Buffalo Lake. And in the next part of this video, and I'll show you the sediment transport model for this study area. That's why I have selected, because I have the measured sediment data for this lake and the unsteady flow data as well. So I'll share with you the bathymetry or the cross-sectional data that I have, and you can open it and you can follow what I'm gonna do right now, so that you can learn how to set up any unsteady flow model in a HEC-RAS, because by this time you know how to create cross-section, right, from survey data if the data is in Excel file. In my first video I have already demonstrated that one, so you can go back to this video if you missed that. It is there. I'll give you the link, and I'll provide this link in the description below so that you can download this cross section and you can even import and you can test. Okay, so what type of data I have, and I'll show you that one. Let me quickly go back to this directory where I have this data, unsteady flow data. So I'll give you that file. Basically this one is a geometry data, and I'll give you this flow and sediment data as well. This data will be necessary for sediment transport model as well. So we have this type of flow data. We'll use this one today. We have the time series flow data. That's why it is unsteady flow data, and if I plot that, it is looking like this one. We have this daily data from the 31st of October 2011 to 31st of October 2012, right? So we have data flow rate in feet cube per second. That's why we have to use US customary unit. Okay, so let me quickly open HEC-RAS 6th version. This is the latest one, and I already demonstrated how to install, right, download and install HEC-RAS. So maybe you already have that one. So what I'm gonna do, I'm gonna create a new project at the very beginning, and I have to find where I have to save that. I'm gonna save everything there where I have that geometry file. It should be there within this HEC-RAS unsteady flow, and I'm gonna give the name as unsteady. Okay, unsteady flow model. Okay, unsteady flow model. So that is the name of my project, and if I click OK, it is gonna ask which one, right? Is asking about our US customary unit or not, because I'm gonna keep it. So US customary is our default one. And what I have to do, the next step is to create the geometry, right? You know that very well. So since I already have that geometry that you'll also have, I'll give you that. So I'm gonna click file, I'm gonna import that. I'm not gonna even waste time to import this data from Excel file, because we know how to do that, right? So I'm gonna import. This time you can't even open using this way. You have to import it, this geometry data, if you have this data in different GIS format or even different format, because this data is in HEC-RAS format. So I'm gonna click that one, and then you can see this right name of the file activated there. If I click there and you have to click OK, then it is gonna ask what will be the unit. We know, right, the unit is in US customary. Click next, and it is gonna ask you some other streamlines and other imports. I'm gonna click next, and then it is asking that okay, we have other stations and other informations and cross sections, breeze and everything, right? I need everything. Okay, and finish. I'm gonna finish it, and then we have this survey data, right? This is pretty appropriate we have. And if I just want to run this model for this one, we can do that. And even we can, what we can do, even we can interpolate if we need. But since this is artificially constructed canal, we don't need to even interpolate, right? We'll do that while running this model as sediment transport model. So the next step, we have this geometry, then we have to save this geometry, and I'm going to save it as different name. I'm going to give the name as Unsteady, okay? Unsteady, wait. So Unsteady geometry, okay? And that will be saved there. It will be there. Okay, so we are done with that one. So what I have to do, the next step is to create the flow data. So previously for steady flow data, what we have done, right, this one, steady flow data. But now what we have to do, we have to create this unsteady flow series, because the flow is changing with time. That's why it's called unsteady flow data, right? We know that if the velocity, flow rate, and the depth of water will change with time, then it is called unsteady flow data. Otherwise it is steady. So time is the main criteria there, okay, in terms of here. And if we want to run the model as sediment transport with unsteady flow, then you have to run this quasi unsteady flow data, okay, quasi unsteady flow. So we'll do that in the next tutorial, next part of this series, in the next, okay, next time we'll see that, not a problem. So I'm going to select that unsteady flow data. This time it is only the unsteady flow, pure unsteady flow model. And here it is for unsteady flow model. See the very upstream cross section, you can see that it is going to give us, will provide our, if we click there, boundary condition, it is going to give us these three options: stage hydrograph, flow hydrograph, and stage or flow hydrograph. So we have our flow hydrograph, right, the time and the flow rate. So I'm gonna click there, that one, and it's gonna open this one. So what we have to do, we have to select that start time, right? We can select that, or we can automatically get that one. How can we get that? If you want to select this way, we can get that. Otherwise there is another way to get it automatically. So that will be, I can show that one as well. So for the first time, I'm going to show you this one, not a problem. You have to select this one. If you select simulation time, then you have to fix your simulation time first, then it will automatically select the simulation time. But since I started with, right, flow data, so I'm going to import my file first. So it will be 2011, and it is October, right? October 31st start time, and it should be 00 because we have the daily data, and you have to select that one as day. But you can see here it is gonna go up to 100, right? So you have to select the number of ordinates there, otherwise it won't create that 360. So how many we have? We need like 367, okay? Then we'll get the appropriate, right, 30, see, 30 first to that one, okay? And I'm gonna copy that data from here, only this column, because we already have the date column, otherwise it won't plot anything. And if you wanna paste it, click there and paste it all together, see? And let me check it. Yeah, it's matching with date and time. And then if I want to plot it, it is gonna plot, and if it is okay, then it's gonna show the same plot we have in our Excel, right? These two are missing. That means it is correctly imported, the same plot we have here. That means our flow data is okay. This is the upstream boundary condition we have here, and what we need, right? I'm gonna click OK, and we already imported this one here, the upstream flow data. And what we need our downstream boundary condition there. So in order to do that, what you have to do, you have to click there, and then see, now we have another, you can even provide the same stage and discharge curve there, or flow hydrograph, or a rating curve, or normal depth. So for this case, I'm gonna provide normal depth. So usually what we did, or what we do, right, we provide this normal depth as a gradient or slope. So it will be 0, 0, 0, 2, 3. So you can use that same value I'm gonna use here. That is the downstream boundary condition. But for steady flow, what we did, we use known water level, right? We already calculated the flood frequency analysis. we perform that one, and then we find out, right, what is the 100-year retain period. But for this case, to be on the safe side, we are going to use this normal days as our downstream boundary condition. So that is the normal practice, so keep in mind that one. Okay, so we are done with our boundary condition. We can save that unsteady flow data. So what will be that one? Unsteady flow data. Okay, so that will be unsteady flow data. So we are done with this one. So it is pretty simple. The model, if you have the geometry, your model setup won't take that much time, but since the model is going to run for 1 year, it is going to take a lot of time. Okay, and then we'll see pretty nice plot this time, and animation as well. At the end of the video, you can see that. So we are done with this one. We can close that. What next? So we need to even import our run condition, right? We have to generate that one. So we are done with our unsteady flow data. We're done with our geometry. We're done with our project. We need our plan, right? So I'm going to create this unsteady flow analysis this time. And when I'll run the sediment transport model, I'll do that. When I'll run water quality model, I'll use this one. And at the same time, I'll also use hydraulic design function to calculate the scour, right? Different types of scouring. We'll do that, not a problem. So this time it is only unsteady flow analysis. And what I have to do, I have to create the start time and ending time. So what is the date? It is 2011, and I saw that it is starting from October 30, right? I saw that the beginning is October 30 and the starting time should be 00 hour, and the ending time should be October 30, 2012. Okay, then we'll have the complete 1 year, and the ending time should be same. And then we have this one, and we can see the output options. You can select that one. The computational time interval is 1 minute. I'm not going to do that. I'm going to select it as 5 minutes in order to reduce the computational time, and you can use 1 minute. 1 minute is also good time. And what will be the output interval? 1 hour, right? And detail output interval. Okay, we can keep that, not a problem. Or even we can keep it as 1 day. That is also good because our time series is daily. And mapping output 1 hour, not a problem. And here, what we have to do, we have to even check this. Okay, it will check the geometry preprocessor if our geometry is okay or not. And then it will also check on a steady flow simulation. I'm gonna check that one. For sediment transport, we have to use this one, and it will do also the post processing. But we're not gonna select this one because this is basically for floodplain mapping. If you have any DEM data and if you run your model as 2D condition, then we need to turn this on, and we'll do that while running our 2D model using HEC-RAS. We'll do that in future videos, so don't worry about that one. So what we have to do, we have to go to option, and in order to check the flow distribution, right, as a nice plot, so we have to check, right, if change this to 8, or even you can change it to 10, 15, whatever you want. And these are the global variable I'm going to change. And then I have to save the plan, right? This is the unsteady flow plan. I'm going to save it. So what will be the name? Unsteady, okay? Unsteady flow. Unsteady flow. And what will be the short ID? Unsteady. I'm going to give unsteady 01, okay? So that's it. And we are done with our plan. If I just try to compute, then it will check. If everything is okay, then it will start running, and it will definitely take a few minutes to run. I don't know how many minutes it will take, but let's check if it is gonna finish quickly or not, because I already just defined 5 minutes. So it is gonna run for entire 1 year, right? So let's check. It's gonna check. See, we have some error that interval for detail output is less than the hydrograph output interval. So we have to do that, okay? So you can check. It is very good model that is gonna give you everything, right? You can check it, and we have this problem there. So the time series data starts after the simulation starts. That means time series data starts after the simulation starts. That means our time series is not accurate, right? What you have to do, go back and check your flow data. This is how we have to be able to read, right? How to read this error and how to solve it. If you go there and if you just click there, you can see the time series data. It is October, right? It started with this one, October 30, 2011, and the date is this and the time is that, and ends October 30, right? There, okay. So it's okay, and the simulation time, everything looks okay, and I'm gonna cancel it. So here it is. If you wanna change the run condition, there, we're done with this one, the run condition. Here, if I select not 30, we can select it like, oh, it should be 31st. Okay, it's 31st, and it should be 30. And let's see what we're gonna do here. And it's gonna be detailed output. Oh, this should be also 1 hour, otherwise that's why, because this time was higher than this time. And let's say I'm gonna save it, save plan, and let's compute this time. Yeah, hopefully it's gonna run. See, it's checking the geometry. If everything is okay, it started simulating. See, the time is gonna take, and you can see the time here, right? The time of simulation and the iteration it is doing. The first iteration we have, and we are not gonna run any 2D iteration here. If your model is for 2D, then it will show you the 2D iteration as well. The first, the geometry preprocessor, it finished, right? So that's why it's showing finished, and now it's gonna calculate, right, on a steady flow simulation, and then after the simulation it will test that one on a steady post processor. So this is how it's gonna show you all these steps and calculation. And if you run your model for smaller time and stuff like 1 minute, so it is gonna take a lot of time. And if you run the model for several years, so it will take more time than expected. So it depends on your computer speed and your RAM and as well. See, it's finished, and it's gonna show you the message that we are done with everything, right? So it's finished with 1 minute, and if you just reduce your time from 5 minutes to 1 minute, it will take more than 10 minutes to finish. Okay, then the number of computational time step will be like how many times? It will be 3, like it will be more than what we have here, multiple times than this one. So I'm gonna finish it here, and let's check. Okay, I'm gonna just quickly show you the output of this model, and you can check everything there. We also have the same output, right? We have previously for each of this. You can see the elevation. These are in feet because these are basically in hill tracks. So that's why the elevation looks pretty high compared to our, and you can, right, the previous videos we saw. That is not a problem. And here, the most interesting part, we can see the cross section, right? Here we can see the cross section. And if you want to see the velocity plot, how can we do that? Here is the velocity plot. We can see that's pretty nice plot we have. And here, click there and go to options and the velocities. Not the velocities, the profile we need, right? The variables we have to, it's there. And then the profiles are velocity distribution. If it is there, it is already there. It's going to plot everything. So that's that. It's going to show you this velocity distribution, right? And what happened here, because while running this model, let me check that. Here it is on a steady flow analysis. Maybe I didn't check that flow distribution locations. It's already there, okay? It's already there. We have selected this one, that one, everything looks okay. Okay, so we're done with this one. So let me show you that. The velocity we have here. And then maximum range of plot. No, we don't need that. We're done with everything. Okay, so we have this velocity distribution, and we can see here we have different options, right? Because this is the constructed, artificially constructed canal. There, so you can see the trapezoidal section, right? So basically for this type of canal or channel, we don't need that type of, these are leg section. So these are the artificially constructed canal or channel. We don't need basically that much interpolation because it is same for everywhere, right? So that's why you can see the velocity kind of same. Okay, so what next? We have to go to our profile plot, right? Here it is, and you can see the water surface elevation and other information, and I'm going to show you the animation right now. If you want to see, click there and it's going to open this window. It is going to start from the beginning, right? You can see on the right side, that is basically the left side of the plan, and the left side here in this plan, this is the big lake. So that one basically this Lake St. Martin, this one basically this is the big Buffalo Lake, and water is coming from this side in this plot. But in the geometry we saw that way, right? It was the opposite of that one. Not a problem. And if you want to see, that is the animation, right? You can see the time here, right? You can see the time. It's from starting to end. Can you see that? Yeah, it's pretty quick, right? And if you want to reduce the time, you can even select there, and you can even see minimize the time, and it will be like less than that. Okay, here it is. Maybe it is so slow to see animation speed. See, it's gonna show you the time. Can you see that? It is slow, right? Slowly increasing and decreasing if you want to see that. Otherwise you can increase the time, the speed if you want. If you put it there, it is gonna be speedy, right? See? So this is how you can see, and you can record. We have the option, you can record the animation here. If you click there, it will be recorded, and you can even display while presenting your project. So this is how you can set up any unsteady flow model. It is basically the boundary condition, nothing else. And you can even change your roughness, and definitely we'll test that in our sediment transport model, and we'll test different equation while running our sediment transport model. So that is another issue. So setting up the geometry sometimes takes time. Otherwise, once you have the geometry right away, you can set up your model and you can run it quickly. And another one is the time, right, we need. So what I'm gonna show you right now, I'm even trying to interpolate the geometry. We can do that. Otherwise, we can even run the model with lower time steps so that we can see what it is going to show you, and it will take a lot of time. Okay, I'll show you that one, not a problem. But before that, I can show you other necessary plots we need, right? The profiles we need, these are the profiles, because see, you can see the profiles, the long profile you have. Based on this thing, you can decide which one is the most appropriate one, and that is the rating curve we have here. And what else we need to do for unsteady flow? We can even see from the view the perspective plot, right? That is the most important thing we need to know. And here we can see that a lake, a big Buffalo Lake here, and on the left side you can see that St. Martin Lake, right? And you can change so that you can easily visualize. Okay, no, not this way, but we need to see, keep it that way, because okay, see, that is the actual scenario. That lake is pretty big. That lake is pretty big, yeah. So here it is. See, water is gonna flow from this lake to this canal, and it is similar to this plot, right? This one. So water is flowing from this Lake St. Martin to that bigger lake, you can see there. And then we have constructed that canal, and we're testing if it is appropriate to carry water without sedimentation problem or erosion problem. So we'll test that in the next part of this video, not now, but in the next part of this tutorial on a steady flow, because that is also on a steady flow, and we are going to run the model for the same condition. We just run this model, and we'll add our sediment data, because we already have our sediment data here. I'll give you this everything. We have this suspended solid, and we also have our bed material. We need that. Okay, I'm gonna upload this all together so that in the next video I won't need to upload it again. You'll have the geometry, you'll have this data, and I'll show you how to add all of them, and I'll run the model and I'll show you that. And here it is. If I wanna even animate there, you can see it's gonna show you the flow. If I hit it, right, see, it's gonna even show you the plot. See, it's increasing. It is gonna show you for 1 year. You can check the date. It is pretty fast, right? And water is flowing from left to right, and you can see the change in water level on this big lake. So this is how we can change your plot, and you can even record this animation and you can show them, right, that okay, this is my model and it is like a live model we have. But for a steady case, we won't have, right, this type of animation because the flow rate is constant for the time period we have. We don't need to specify the starting time and the ending time. That's why that is called steady flow, and this is why it is called unsteady flow here, since we have time and the flow condition is changing and it's basically varying with time. And there will be another flow condition, uniform and non-uniform. Definitely this is not uniform flow, but we can consider this one as uniform flow. For most of the open channel flow, we assume that okay, these are uniform or non-uniform. That is another part of discussion. So this is the way we can display our result. We can record, we can do this thing, we can do that thing, and we can even see our cross section. I already mentioned that one, right? Because we already have everything. See the roughness, and we can change the roughness and everything we have there. And even we can copy. So these are the artificial canal. So that's why we don't need different types of information, right? We have only 4 values, this value, that one, and this. We need only 4 points. Then it is kind of trapezoidal, and we know that, right? The equation for trapezoidal equation for trapezoidal cross section of a canal. So you can practice by yourself, and yeah, definitely it will work. I'll give you this geometry so that you don't need to even import all this manual job. You don't need to do that. And last time I'm going to show the effect of time step, right? That is what I was trying to say, that what will be your time step. So at the same time, you have to reduce the time step and you have to improve the accuracy of your model prediction. So for this condition, we have our observed data, and we'll check with our observed data. And I'm not going to do that here right now. I'll do it for sediment transport model. We'll test because we have our observation sediment density, and we'll check if our model is working or not. That's why we'll calibrate our model. We'll do that. We'll calibrate our sediment transport model because we have our observation data. And here, the main thing we need to know, if I just reduce this time step from 5 minutes to 1 minute, right? And you can even go to 0.1 second. I'm not going to do that. So the default one is 1 minute. And if I run this, you'll see, right, what is the time step. And I'm going to hit, see, it's going to check the pre-processing. Everything is okay. It finished pretty quickly. There is no error, but you can see that it is not even gonna see 1st of November. It's just running for 4th of November. Can you see that? It's gonna take a while. And even though the calculation, because it is computer running with 16 gigabyte of RAM, and the ROM is pretty big, so that is not a problem. And the processor is Core i7, so it is taking a while. And you can even run this model if you're familiar with Linux machine, and if you have any Ace PC, high performance PC, and you can run that one as well. They have this Linux version of this software package, so you can run that as well. That is not a problem. So previously, can you remember that? What was the total computation time? I can remember it is 1 minute and 6 seconds, but this time I think it's gonna take a few minutes, so it will be multiple times. But for this regular cross section of the channel, you don't need that, because we're gonna test our cross section, right? That's pretty regular. So whatever time step is, it won't change that much. So that's why you don't need to even reduce your time step in order to increase your computational time, and it is just gonna create a bunch of data. Your output will be, right, output volume will be big. You don't need that because it's gonna repeat the same thing, and we can see, right, pretty quickly we can see what will be the output of this, and we can see the animation as well. Then we'll be ended up with this tutorial. In the next tutorial, you can see by this time what we have here, right? We have the bed material, see the percent finer, and people just collect the bed material from multiple location, and then they use that sieve analysis to plot this, right, this graph distribution or gradation curve, and if your particle is so fine, then that sieve analysis won't be effective, right? That's why you need to do the hydrometer, right, analysis. That is another test for the finer particle that is smaller than 200 sieve. So you need that hydrometer test. So that is another use. And after that, see, we also have that flow, right? This is the flow rate, and we have this outlet like buffalo, the big one. The outlet of that, we have this total suspended solid milligram per liter. So we'll validate our model, we'll export the data from our model, and then we'll validate using these values, because these are the measured data. Then we'll also see the bed change, right, within 1 year after running this model with this bed material. What will be the effect? We'll check that, and then we'll make sure that, okay, this canal is gonna be stable or not. So depending on this situation, we can take decision, right? So see, still it's running, and maybe it's only the halfway, not even it's done. So can you see that when the time step is 5 minutes, it was like 1 minute run time, and when it is 1 minute, the run time is like more than 5 minutes or 10. I don't know, it is gonna be more than that. It's pretty fast, and still it's running. So when it will be done, then I'll show you the animation, and then you can check that there is not that difference between the previous one and this one. But for other cases, maybe it is useful if you have a natural canal or channel and you need to optimize, because these are basically the prismatic canal, the regular shape of the canal, right? We have it is artificially constructed, we call it prismatic canal. And if it is non-prismatic, means the natural canal, then you need to even use that minimum time step, then your model will be stable. So we have to test this time step. That's why I'm going to show you this one, because we'll use different time step for sediment transport analysis in order to make the model stable. Otherwise, when we'll add our sediment right data, then the model maybe it may be blow up, and there will be different issues. So that's why we have to test with different time step, right? Because it is solving the differential equation. Unsteady flow, for unsteady flow or steady flow, whatever it is going to solve that differential equation. And if our solver is stable, if the model is stable with the appropriate boundary condition, the flow data that we have provided at the very upstream and the normal depth at the very downstream, because it is going to match, right, the downstream boundary condition, it is going to create that one 0.00023 from that upstream boundary condition. And in order to match that, see, it's this time, it's multiplied 5 times. That's reasonable. Okay, so I'm closing that one, and I'm gonna show you the animation one more time, and let's see what we can see there. If I run that one, it's gonna start from the beginning, and here it is. Can you see that? Yeah, see the flow rate and everything. It's gonna show you this way. So that is the output of this model. So there is no change. I can't see anything. If you can see any difference, let me know in the comment box. Then see, it's increasing and increasing because we have the peak, right? You see the peak, and the changes will be there when the peak will arise. So that is the impact of the flow, and we have to test the impact. See, drastically it increases because we have the peak. We can see that, right? In the simulation or in the data set, we have the peak there. So that's that. See, it's gonna increase, and now it is this one. The time is this after June and July, and then it will just reduce because after that we don't have that much flow. Okay, so I'm gonna end off here. So try by yourself. I'll upload this data, and then let me know if there is anything wrong, because that is the most complicated model in HEC-RAS, and the sediment transport, it will be more complicated, and then I'll show you in separate videos about how to set up any model that is water quality model. Okay, I'll do that, not a problem. So thank you very much for watching, and stay safe, and stay safe until then, and see you in the next tutorial. Bye.